Hello, everyone. Good morning. Good morning. Everybody does this, right? Everybody does the good morning twice, so I had to do it. My name is Manu Fontaine. I'm the founder and CEO of a public benefit cybersecurity startup in the Northern Virginia area, just outside of Washington, D.C. I must tell you, I'm genuinely excited to be here. It's my first time at Identiverse, so yay, first time attending, first time presenting. So thank you for having me. Thank you for attending this talk. I look forward to connecting with as many of you as possible. We think this is a very important topic, and we'd like to connect with as much of the industry as possible. I want to talk to you about personal cryptography for two reasons. The first one is that cryptography underpins all facets of digital security, not just identity and authentication. Think about data security, data provenance, right? The data integrity, privacy, confidentiality, delegation, vouching, voting, reputation, transactions, you name it. All of these things rely on cryptography. So if we can solve for personal cryptography, whereby two entities, completely unrelated, human or non-human, that can be anything, if two entities can have exclusive agency over their own cryptographic keys and cryptographic primitives, then we can get to the holy grail of creating completely seamless, completely frictionless, completely cryptographically secure experiences at global scale across domains, across supply chains, across clouds, across metaverses, you name it. All of these things become possible if we can solve that problem of personal cryptography. And again, I use personal, it's not just humans, it's virtually anything. And the second reason I'm particularly interested in and excited to present this at Identiverse is that the solution to personal cryptography turns out to be a new namespace, a global namespace. We call it the Cryptographic Name System, the CNS. We had the IP addresses at the network layer. We had the domain name system at the domain layer. And the Cryptographic Name System is our way of talking about unique identifier for each and every entity in the physical world, in the metaverses, wherever you want. So kind of a universal name system that works across everything and that enables cryptographic security for virtually any application. And of course, all this is great, but personal cryptography is only useful if it's usable and trustable by everyone, which is why we're going to talk about consumerizing it. And what that means really is that you have to automate everything. You have to remove all humans from it, and you have to make it invisible, because people should never be exposed to cryptography in any way, shape, or form. Seriously, right? And then because we're going to automate key management on behalf of the entities, we need to also bring hardware security all the way to these mainstream users. So we need to consumerize personal hardware security module, it's a mouthful, personal HSMs, and we'll get to that in a little bit. So I'll show you the blueprint about how we get there. But before we actually talk about the how, we need to talk about the why. And I think you're all going to agree that we don't just have an identity crisis. We have a whole bunch of unresolved issues, right? Data security, data binding, exclusive agency over data, attack surface that is ever-growing. It's a huge mess that we have out there. And right now, it's turning into a global cybersecurity crisis. And for digital economies that are quite advanced like ours, like in the US, this is turning into a national security problem. And the numbers are just staggering. We're talking about trillions of dollars at global scale in cyber fraud, in spite of hundreds of billions of dollars in cybersecurity spending. In the US alone, the number is estimated to be over $1 trillion. Do the math, there's about 330 million people in the US. That's $3,000 for each and every one of you, including your kids and your parents and everybody. $3,000 per year of cost, 5% of GDP that is being drained out of the economy. And of course, the scope of this is like mind-boggling, right? Over the next decade, tens of billions of devices will connect to the internet. will permeate the lives of billions of people. Everyone's going to have an expectation that, hey, it works just smoothly, it's perfect, it's secure, and it's frictionless. So we have a massive problem ahead of us. And I would suggest that we need a unified internet scale approach to this problem. We need to stop thinking in terms of our little problems in our own domains. And our friend Steve Wilson has a great way of summarizing this, that data is the next utility, as critical to society as clean water. You never have to think twice whether the water you take from the tap is clean or not clean, whether you can drink it or not. Imagine your life if you had to do so. So we need to do the same thing for data. And Steve is basically coining the term, infrastructure, information infrastructure. And when you translate what that means, it essentially means that we need global assurance of data provenance and integrity for everything. And if you translate that, you realize that what we actually need is global chains of data custody. We need to know that every time the data moves from one place to another, it's being handled properly by the right custodians and that only the right entities have access to the data. So global chains of custody across domains, across supply chains, across everything. And of course, the elephant in the room is that if Alice and Bob are trying to exchange data or transact, it's the domain. We have a domain in the middle. So I propose that we don't just have a man in the middle, a woman in the middle problem, we have a domain in the middle problem. We basically just create those local identifiers, we put data in databases, we strip agency from the entities that the data belongs to by giving it to the admins who run the domain and run the system, and the attackers who get in. And then by putting data in databases, we create weak relational bindings between the data and the identifiers of the entities that represent, the data belongs to. And of course, because everybody is doing the same thing over and over again in different domains, we have that constantly growing attack surface that we can't tame fast enough. So here is the provoking thought of the day. Domain-centric identity management is the elephant in the room. It is the root cause of many, many of the problems we have. And so I suggest that we need to move from IAM to an approach that respects who I am, an approach that respects the integrity and the agency of the entities that are being represented in our systems. That's where personal cryptography comes in, because it will enable to restore cryptographic agency over keys, over data security, and data bindings. And if we could have some technical help, that would be great. I think we lost a technician. And that's really too bad, because the next slide is really, really nice. And I can't even turn the screen. I put so much work in that slide. Thank you very much. Somebody didn't like the presentation. It's showing on that screen, yeah. It's the fuse over there that just blew. So anyway, I think I'll have to keep going, otherwise we're going to run out of time. Hopefully this is going to be in the recording. So I have a wonderful image of Wile E. the coyote holding sticks of dynamite in its hand, and the slide is basically saying that cryptography is absolutely unforgiving and that humans are hopelessly unreliable. So you can't let humans touch cryptography. It's going to blow up in their faces. But there's a more interesting or more subtle aspect to it, which is also that cryptography is implementation and operations dependent. It's not good enough to have open standards and open libraries and open source code. It's the way you implement the cryptography and the way you operate it that makes it reliable. And so the problem with all the self-sovereign cryptography, the self-sovereign identity and all that, something that nobody talks about, is the fact that the cryptography itself needs to be strong, healthy, and cryptographically reliable in the sense of relying party. So I will keep moving on. We have Alice and Bob, our two antagonists, and how can we have them communicate with one another? I'm going to make gestures. Alice and Bob, they're trying to communicate. The first step is that they need to delegate. They need to relinquish doing their own cryptography. And they need to delegate that to a cryptographic agent a personal cryptographic agent that we call a cryptographic twin. You heard about digital twins. Our twins are cryptographic, and you'll see how we actually build them up. And Alice's twin has an exclusive relationship with Alice, and Bob's twin has an exclusive relationship with Bob. The exclusivity of that relationship, of the bond, is ensured by the twin itself authenticating the entity. So there's no centralized authentication. Each twin authenticates its own entity. But that itself is not enough, because Alice's twin, I hope you guys can visualize this. Alice's twin, do you think I don't know, it's all taped in. I don't want to, and it's, yeah, it's only going to work for the guys who sat in the front. That would be a good, yeah.
No, we like your description.
Great. Oh, great. So I continue. Okay, so I said Alice's twin and Bob's twin, right, are trying to establish a relationship. We want it to be automated. We want it to be completely invisible and seamless. Alice can't do that unless she knows that Bob's twin is cryptographically strong and healthy. Conversely, Bob's twin should never enter into a relationship with Alice's twin if Bob's twin doesn't know, has no way to know whether Alice's twin is cryptographically strong and healthy. And the solution for that is verifiable cryptography, not verifiable credentials. We're talking about one level deeper. The cryptography itself must be verifiable. And that can be achieved with remote attestation. I don't know if you guys are familiar with remote attestation, but that's a feature and a capability that comes from confidential computing. Confidential computing, there's two flavors. And again, the slide is very nice, but hey, I'll send you the slides later. There's two flavors of confidential computing. There's the cloud version and the IoT version. The IoT stuff, we're going to come back later. Microsoft Azure Sphere. I don't know if you know. Anybody has heard about Azure Sphere before? Fantastic. Yeah, one person. Great. A couple of people. That is incredible. You guys should definitely go and check it out. It's an IoT chip that is remotely attestable, that is confidential computing, capable or like. And so we'll come back to this when we talk about the personal hardware security modules. But at its core, confidential computing is cryptographic security at the hardware layer. So the silicon itself is capable to assess its own integrity, to measure the software that runs on it, and then to sign this with a key that is burnt into the silicon itself, so it's tamper-proof, and then send that assessment to an attestation service. And so imagine now, visualize the twins running on confidential computing chips, those chips being attested through a remote attestation service. Now the two twins don't have to worry about anything anymore because they know that Bob's twin is compliant and cryptographically strong, and conversely, right, Alice's twin has all the same properties. So now, really unfortunate, you can imagine, you can visualize in your imagination a first link of a chain of data custody where two twins representing two entities are able to transact and have established a cryptographic relationship completely automatically. Now, if you zoom out and you imagine every entity in the world or in the metaverse having their own twins, and every twin running on a confidential computing chip, and every twin being attested, now you zoom out and you see it's no longer kind of a domain in the middle topology. It's a mesh network of cryptographic agents. And all those agents can, at will, create a relationship with any other twin because all twins are running on confidential computing machines. So they don't have to ask themselves a question. They can just go ahead, exchange keys, create a cryptographic relationship, and can transact from there on. And from that high-level topology of a mesh network, you can then go to the next level and realize that, OK, so you can now stitch together those chains of data custody where the entities and the twins that need to participate within a user experience or for a specific transaction can automatically put in place the relationships that they need and transact secrets or whatever signed documents or secure information within that chain of data custody. And that would be true if and only if we can solve the binding problem. So everything I've told you now, right, is assuming that the twins have exclusive agency over all the data that belongs to their entity. And if we introduce at this point traditional GUIDs, globally unique identifiers, and a database to put data in a database bound to the twin, we are reintroducing weak relational bindings. And so we can't do that. So we need to do something else. We need to go from GUIDs to a new type of identifiers. We call them STEM IDs. And the STEM IDs have these three properties. The first one is that these are 256-bit identifiers, twice the size of GUIDs. The second property is that those identifiers are truly random. They are generated from within the silicon from a true random number generator. So you have a namespace now, 256-bit, huge. And now I've lost these slides. Wonderful. And the third, so completely random, 256-bit. And the third property is that they're generated within the confidential computing environments, and they're never exposed to outside of those environments. And they're managed within a peer-to-peer network of confidential computing hardware. And so these three properties together make these STEM IDs very unique because they are both identifiers and keys, AES 256 keys, symmetric keys, at the same time. Visualize this. It's an identifier, a random number. It's both an identifier and a key. And what this achieves, it solves the binding problem of a primary identifier for an entity and a primary key, from which we're going to be able to do all kinds of cryptographic operations because it is cryptographically strong. And the operations we can do, for instance, are the twin can now, from the STEM ID, can derive an unlimited number of decentralized identifiers, DIDs. And I'm using that term not really in the SSI sense, but really these are just random identifiers that can be given in different contexts. And then the twin can hash those decentralized identifiers and can put that in a routing table. Now, each and every one of those DIDs corresponds to an entry in the routing table, so the twin can be routed to. There we go. Much easier to visualize. Thank you so much. And then, anyone who, any context or relying party that gets the DID can hash, can find the twin. The twin can generate, I think I'm going to need to speed up a little bit. The twin can then create an unlimited number of keys. We're using exactly the same approach. Those keys can be used to encrypt an unlimited amount of data in an unlimited number of contexts, and then hash those keys, and now you have storage locators for that encrypted data, none of which can be related back to the twin because it's all one-way hash functions. But the twin, knowing the STEM ID, has exclusive cryptographic agency over all of it because it can recalculate all the DIDs, all the addresses, all the keys, and then retrieve the content and decrypt it. So that is what we call the cryptographic name system. It's a universal, truly random, 256-bit cryptographic namespace that works for everything. There's nothing more universal than a random number, right, generated from a piece of silicon that no human has ever seen. And then from that STEM ID, you can derive keys, you can bind data, you can encrypt data, you can bind encrypted data, and you can basically just let those twins then automate cryptography with any other twin. Going back to that mesh visual that you didn't get to see. And then there's one last piece, coming back to the personal hardware security modules. I told you about Microsoft Azure Sphere quickly. Now we have those twins. These are these silicon life forms, and we have carbon life forms. We have humans that need to bind with those twins. I want to have an exclusive relationship with my twin. By physically decentralizing the confidential computing infrastructure using Azure Sphere, for instance, we can create those personal hardware security modules. And what that enables is a human can now bind and roll their phone physically and in person with their personal HSM. So then you can use your phone, you can go anywhere in the world, you can interact with whatever relying party service. The personal HSM can connect to those services, provide cryptographic services to all those services, great. But what's great is that if you lose your phone, you can just get a new one, walk up to your personal HSM and rebind, so recover in a self-service, in-person way. And because the personal HSM was holding the binding and the relationship with the previous phone, the one that you lost or that was stolen or broken. The personal HSM can revoke the old, lost, stolen, or broken phone. So you have self-service, in-person, enrollment, recovery, and revocation of a normal human's phone, right? All of this in person and physically without relying on any other human being. There is no other human in the loop at all. And that eliminates the possibility of social engineering and insider attacks on the recovery loop, which is always the weak link in every cryptographic system. So let's wrap up, and I'm really sorry for the technical problem. Not much I could do about it. We have a global cybersecurity crisis. It's not just an identity problem that we have. The domain in the middle, and I hate to say that because I know that all of you guys and all of us are thinking about domain identity, but that is the elephant in the room. That's what needs to go away eventually. And that is because local identifiers deprive ourselves, steal us, deny the possibility of a global namespace that would enable the creation of those chains of data custody across supply chains, across clouds, and other ecosystems. So we strongly propose that we need to move away from IAM. We need to move to an IAM type model. And we told you about a cryptographic name system, which is the universal namespace, simply because there's nothing more universal than a random number in a piece of silicon that never exposes to the outside world. These STEM IDs then enable the creation of cryptographic twins by deriving keys, encrypting data, and binding it all to the twin. And then those twins can interact with other twins, automate cryptography among themselves to stitch together chains of data custody. And finally, by physically decentralizing the confidential computing infrastructure, the network, all the way to the home of citizens, consumers, employees, you can have that human twin binding that enables in-person, self-service, enrollment, recovery, and revocation. That's it. I think I'm going to go show you the nice slide that I had. Just we can afford this. Of course, it's a little bit long. What time is it? Are we? All right. So you see all that you missed. I worked so hard on all these graphics. Here we go. This is the message to take away. Yes?
So what happens if, what is it, HSM?
Yes.
So HSM is what's binding, right? So we didn't talk about how the attestation is, like, from credentials and stuff. Or happens, we'll leave that alone. But what happens if the HSM is stolen?
So the question is, what happens if the HSM is stolen? So one thing, because I didn't have enough time to just tell you about this, but one thing that, the only way that this can work is if you leverage this automated cryptography property, right, that we designed the system for, to back up the system itself. So what happens is that those STEM IDs, when they're generated for any entity within that mesh network, it gets backed up by other equally trustworthy and equally secure twins that basically just act as backup buddies, if you want, to the twin to which that STEM ID belongs. So if if the personal HSM gets destroyed, no big deal. You automatically move to another virtual HSM, and that's great. And then your question was, what happens if somebody steals it? It's not good enough because your relationship with the HSM is between the phone and the HSM itself. Right, so you need both, and of course we use Face ID, Touch ID on the phone, and then anyone who's on the mesh, right, we would be the first one to notify you because those devices basically talk to the network and notify us in real time if they drop off. And then anyone on the mesh can essentially revoke your HSM. You can get a new one. You can just rebind and recover from there. So the physical decentralization of the HSM is simply an extension of this peer-to-peer mesh network. And it's not, you cannot consumerize cryptography if you're bound to a single physical instance of a device. That's the problem with HSMs, is that if the key is in the physical device and the device gets destroyed, then you're toast. So we had to solve the peer-to-peer backup as a prerequisite to make any of this work. I'll be to you in a second, but yes?
How is what you're presenting here similar or different to the carry protocol?
Very good question. So how is this different from the carry protocol? Carry is indeed a protocol. As I was talking in the presentation here, this is an actual implementation and operational infrastructure, right? So the way carry is implemented already just potentially creates issues with carry. As a protocol, carry is great. It's basically very similar to hashing. The main difference is that carry starts with a seed of 128-bit. We start with 256-bit, which is top secret AES level of security. That's what gives us the encryption layer, in addition to all the key derivations and the hashing. And then the second thing is that carry does not do anything about the actual operational security of the seed itself. Carry assumes that somebody else is securing the seed. And that's what I was saying here. And you can't rely on DIY, right? It needs to be the seed itself. In carry's case, the stem ID in our case, must be secured at all times for any of it to be cryptographically reliable. Yes?
A couple questions kind of all tied together.
Yeah, and I'm more than happy to answer plenty of questions. I really want to connect with you guys. So
Are you envisioning that at some point every individual will have their own one or more personal HSM device? And then how do I authenticate to my device?
Mm-hmm.
And then
Well, so maybe I should take those on offline, but the vision here is, this may end up being built into other products. For instance, we're thinking of, anyone who buys a home and wants to put an alarm system in there. Imagine having, personal HSM built into, the panel for your alarm system. That's one thing. It can be built into other products, but the personal HSM is an option, right? You can still function with a virtual HSM. The problem is, of course, you lose the recovery and the revocation that is all self-service. Anyway, I hope that answers your question. And how you authenticate to it, you bind yourself to it. You do have a PIN, so there's always a what you know factor with your twin, not with the physical device, but with the twin that is hosted there. And then you can add other factors. We could have, FIDO to my twin. All of that works. What we really replace, remember, the whole premise here is that we eliminate the domain in the middle. We enable direct connections between twins and entities. Yes?
For domain in the middle, can we use the good old PGP?
So the whole vision here is to say everybody should have the full benefit of personal cryptography. Oh, yeah, sorry. The question was, can we use PGPs, right? PGP for, I'm sorry. Right, and so what we use under the cover, what would be in here, are the NSA recommended algorithms. So we're not creating new cryptography here. But really, the important piece is that you want to automate it. So you don't want to do, I'm going to choose PGP and somebody else is choosing something else, right? We want to be able to just have data, just like we get clean water from the tap. That's the infrastructure vision, right? You forget about all of it. All the cryptography is automated. All the key management is automated on your behalf. Thank you very much, guys.